Did you find them, Jacob? Okay, good. Hi, everybody, and welcome to the application is basically for Gauss's law. This is the whole deal today. We're going to talk about how we apply it, and we'll go through several textbook examples from actually the textbook. And I also posted 2 problems for you guys to look at, similar to some extent to what you guys have in terms of homework, and also similar in a sense to what you might have also in an exam. So this stuff is important. You really have to pay attention to it. So we have an exam not a week from today, in about 2 weeks from today. Next week we will finish chapter 23, which is basically another way of finding the electric field, but via the potential field, the potential electrical potential, which is not a field, by the way. It's a scalar field, if you want to call it a field. It's a number, and like the electric field, which is a vector. So that's the difference between them. So we will discuss that in next chapter. And we would have basically found different ways, either through direct integration from chapter 21, or through the Gauss's law, through this chapter, or by first finding the electric field, then using the relationship between the electric field and the potential, and then from there we're going to find basically, which is just a derivative, taking the derivatives, except the derivative is in a vector notation, which is called the gradient operator, and that's basically how we can find the electric field in 3 different ways, if you wish. So those are the different methods, and that's the whole test they examine here. For those who came in after basically we started recording, I have put 2 problems. They're actually from the 15th edition. The only reason I'm using the 14th edition, because previously when you took Physics 4A, you were required to do that book. So I stuck with that book in a sense, but there is a new book, and from now on we're going to be using the 15th edition, not in this class though, but in the future for this sequence of courses. So the book is the 15th edition. It has slightly more problems. They removed some problems. They added new problems. In terms of the content itself, there is nothing basically new. We're not doing new research as far as this field. I mean, this has been done a long time ago. So, okay. Okay. So basically, that's the 2 problems I want you to pay attention to. There is actually, in the second problem, there is actually a PDF file added to it, which is basically how to do the integrals for the secant functions. Because you will find that the integrals that you'll be dealing with are secants of some sort. So there is basically the standard method on how to do a secant integral. If you don't care really on how to do the integrals, all you want is just the answer. Put your answer into one of those standard format for the integral and use the answer from that PDF file. So you don't have to actually do the actual integral. Just use the reference that you have in there, or any other reference for that matter, on how to find the integral. So that's something that I added there just to make it from the, what is it, from somewhere in Canada, some university in Canada, I forgot the name for it. From professor there. So that's basically what I used there for you guys, and I put the link for it there too. Okay. So that's basically in a nutshell. Let's continue first with the lecture, because the lecture is really mainly applications, as I said, for the Gauss's law and how to apply it in different situations. So let me share my screen with you guys. Go into my OneNote. So basically, we looked at this situation. We looked at the Gauss's law. We did not really do a mathematical proof for Gauss's law properly, to be honest with you. We used the physics behind it. And we said that this is basically what would happen. The math behind it, there is actually a good reference for this purpose, and that is Feynman Lectures. And I know I put the link for it. There are 3 books. Basically, you can go online. I have actually one of the books in here. Let me see which volume is this. This is volume 2. This is actually the book that you can get also. This is the one that has the proof for it, if you really want the mathematical proof and you're interested trying to find that. But it really makes sense. First, you take a point charge. You find the flux of the point charge going through a sphere. Okay, that's easy enough. Then you say, you know what, I'm interested, what if it's not a sphere in any arbitrary shape? Then in this case, you will have the dot product will involve two unit vectors, one along the radial direction, which matters, and one along the azimuthal direction, the angular direction, and that doesn't matter because the electric field is in the radial direction, and that direction cancels out because of the property of the dot product. That's zero. Okay, cosine of 90 degrees is zero. Now, in the radial direction, as the electric field decreases because of 1 over distance squared, the area increases as r squared, and the two effects basically cancel one another. And at the end, the answer will be irrelevant to what shape you have. It doesn't have to be necessarily a circle. So that's one thing. Now we have done the point charge in any arbitrary shape. Now you ask, what if this point charge is outside of the sphere, actually, in this case, what happened? Or outside of the surface in general. So as long as the surface is closed, if it's inside, you're going to go full circle. You're going to go full cycle, I should say, from 0 to 2 pi. So that's where the 2 pi comes into that situation. But if you are outside of this the surface, you're going to start from some angle, and you come back to the same angle, and the boundaries of the integration will be the same, which means the result is going to be 0 regardless of what the integrand was. So if the point charge is outside of the surface, it's not going to contribute into the flux of the electric field. So that's, we solve it basically, the point charge, a single point charge. You ask now, what if we have more than a point charge? Then we invoke the superposition principle, and we add the two electric fields that are coming from two different point charges, and the net effect, since we know the result for each and every one of these point charges, is just the sum of the charges over epsilon naught on the other side of the flux, basically. Then you say any number of charges, you just add as many as you want. And add as many as you want. At the end, you're going to end up with the algebraic sum of the charges divided by epsilon naught. So that's in a nutshell when you have to deal with the proof for Gauss's law. Now, what if the distribution itself of the charge is not uniform? A lot of the homework problems are giving you basically a different configuration for the distribution problem of the charge that you have to sum, not an algebraic sense in a sum that charge 1 plus charge 2 plus charge 3, but the sum becomes an integral, and that's the end of it. And that we know how to handle integrals. So, and that's what we're going to do today. As a matter of fact, the two examples, both of them have that situation, and also some of the homework problems have that thing in them, which gives you an idea of how the exam is going to go. So the exam most likely will have to do a sum over the charges, and that sum is not going to be a simple algebraic sum. 5 coulombs plus 10 coulombs plus negative 3 coulombs. That we will reserve for physics 10, but for you guys, you'll have a little bit of work to do in a sense. This is calc-based, so you'll have to sum those charges using the integral. Today, we're going to do the example together, and you have homework that are due. And if we don't finish these problems today, I promise what I'm going to do is I'm going to make the solution for these problems available for you on Canvas, so that you can go look at my solution, compare your work with mine, and make sure that it makes sense to you. If it doesn't make sense, or you find that I made a mistake, please let me know so that we can fix these things, okay? By the way, I don't think that the 15th edition has a solution manual already published, so there is a problem there if you guys are relying on some outside resources to find solutions. This problems probably you're not going to find them solved somewhere in there, okay? So that's one thing in here. So that's basically where we are. So basically, okay, let me click somewhere and then click back in, because this thing sometimes does. So we're going to do the electric, this is examples from the book, okay? The electric field for a conducting sphere, okay? Remember, we said that, did we talk about conductors or not? I think toward the end we talked about conductors, that they have free electrons, free charges to roam around. Did we talk about the conductors or not last time around? Anybody? Yes or no? Okay. Yeah, we touched a little bit on them. So we're going to come back to them then and give it proper fair shake, okay? So basically, there are at this point, I mean, there are more, okay? At this point, we're going to divide materials into two classifications: conducting materials, like metals, like for example, a piece of iron, or any metal that you can think of, for example, silver or copper, which is used extensively in circuits or in electricity in general. Those are conducting materials. So basically what they have in this situation, they have free charges available for them. So if I'm going to draw a conducting material, this is how the conducting material would look like. For example, this is a cross section from it. This is, or if you wish, that's a 3D shape that has an arbitrary potato-like shape, okay? So it's connected, okay? And this has free available charges, charges that can move at will, I mean, freely. As long as there is a force exerted on them, they're easily movable, okay? Electric field will result in a force. So for example, if the charges are sitting in an electric field, this is the force with which they are going to be subject to, Q times E, where Q is their charge. So these charges are available and available to move, to be subject to this force immediately. In a conductor, these charges can move easily, okay? Easily. And like in an insulator, it's very hard to move charges in an insulator. That's why, for example, you cannot use a piece of wood and connect it to the battery and expect charges to move through the piece of wood, because the wood is an insulator, so it's not going to conduct. The air, for example, around us is also an insulator. If it was not insulator, any charge anywhere will travel everywhere, and that's a problem. For an insulator such as wood or air, you really need a lot of charge to conduct through it. That's what happened during lightning, actually. The charge builds up in the cloud so much that there is a huge potential difference between the ground and the earth and the cloud, that at that point, charges will break the air and discharge, okay? As long as we are not in those extreme situations, an insulator will not conduct electricity because the charges are anchored to their molecules or atoms. They cannot be easily moved, okay? And like in an iron, for example, it has electrons outside that do not belong to a specific atom, but they belong to the entire basic community of atoms of iron. So if there is an electric field somewhere, sorry guys, I don't know what happened, okay? For some reason,
Yes, sir.
yeah, okay, sorry. Okay. Okay, if this happens again, we probably have to fix that. Okay. I don't know. This is the first time it happened today, or at least this entire sessions that we're having in here. So let me continue with the argument that we were doing. Okay. Okay. So if there is a, did we lose it again? No. No, I'm have to share my screen, I suppose. Okay. Okay. So if there is a charge that can makes it inside the conductor, so I'm assuming this is a positive charge, as I was saying. So if there is a positive charge that some of it goes inside, then in this case, these charges will be free to move. Okay. Before you do that, these charges now, they will again create their own electric field. Remember, the electric field is Q over 4 pi epsilon naught divided by the distance squared. So there will be an electric field inside. Since there is an electric field inside, these charges must move somewhere along the direction of the electric field. Let me take this, the direction of the electric field. Okay, so the charges start moving. Okay. And when they do move in one way or the other, depending on which way the electric field is pointing, then in this case, they cannot basically at the end escape the material, and they will end up basically on the surface. In other words, the electric field must be zero inside the conductor. Okay, so that's one thing that we needed to understand a little bit, and it all has to do with Gauss's law. Okay, so there cannot be an electric field inside the conductor, because if there is an electric field inside the conductor, the charges will move. You guys understand that? If E is not equal to 0 inside, the charges will move inside. End of the story. Okay. Now, if this is basically while they're in transition, they might be moving, but at the end, they will stabilize. And once we reach static, then there is no moving charges, which means the E has to be 0 inside. And if E is 0, if I apply Gauss's law, the flux must be 0 because E is 0. And since E is 0 and this is equal to the charges enclosed, so Q enclosed divided by epsilon naught, which makes it that the charges enclosed are 0. See, there's this argument, and I'm sorry, I was thrown off by this thing that went out in terms of the internet. So there cannot be an electric field inside a conductor. Why? Because if you tell me there is an electric field inside a conductor, then the charges will move. Okay. Since what we're saying in here, we are in an electrostatic condition when nothing is moving, then the charges cannot move. Therefore, there was never to begin with an electric field inside a conductor. Since there was never an electric field inside a conductor, take any surface you like. This is a closed surface. Take any closed surface you like inside the conductor. You will not have charges inside. Why? Because there is no electric field inside the conductor. Therefore, there is no charges inside. Do you guys understand? So forget the argument I was trying to make earlier, because I was trying to. Let's repeat the statement exactly on how we arrived to this conclusion. There cannot be an electric field inside. Why? Because if there was one, charges will move. Basically, no charges inside. So the answer to the whole thing is Q is equal to 0 inside the conductor. Okay? Q is 0 inside the conductor. But you dumped some charge outside on the conductor, so that charge cannot be inside. The only place it can be is on the surface. Okay, so the charges on a conductor can only exist on a surface if they exist at all. So that's the bottom line. Okay, does this answer your question, Kyle? The argument is the following. We cannot have an electric field inside a conductor because by definition, a conductor has free electrons to move, free charges to move. Okay. Now, if there is an electric field, they will be moving, and that is not electrostatic condition. That is not the stationary condition for the charges. They are in motion. Because we're arguing that this is an electrostatic condition, then charges cannot move, which means that the forces on them are 0, which means that the electric field on them is 0. So there is no electric field inside the conductor, which results in the fact that then if I apply Gauss's law, because remember the Gauss's law by definition is the integral of E dA over the surface. And since E is 0, the flux is 0, and the flux is also, per Gauss's law, is the sum of all the enclosed charges. So there is no enclosed charges, or if they do, they cancel mutually. Okay? So at the end, the net charge inside a conductor is always 0, no matter how much charge you dump on it. It's always 0 inside the conductor. So you ask, where did the charges go? The only place they can go, if you dump charges on it, they go on the surface. Okay? So that's an important result, because we need to have that for later on. I mean, this explains also some of the experiments that people do with Faraday cages, and it happened to me. Actually, I was in Canada a few years back, and there was a storm basically, and the lightning hitting every which way, and we were inside the car. That was the safest place for us, because it's made of metal, and that was basically the one to protect us. Because again, metal will not have charges go inside, it's going to have them outside on the surface. Okay. Make sure you don't touch the handle or anything like that, so that the charges will get themselves to yourself, to your body. So that's basically one of the results that we have to use. And in here, example 22.5, it says we place a total positive charge on a solid conducting sphere with a radius r. Find the electric field in a point inside or outside the sphere. Okay, this should be easy to answer if we do the following argument. So we have a sphere now. This is not a circle, this is a sphere. And we have a Q charge on it. So where is the Q charge? It has to be, even if it's a solid sphere, okay? This is not a hollow sphere, this is a solid sphere. So but as long as it's conducting, and the problem was saying it's conducting. So the charges must be on the edge, they cannot be inside. And the question we're asked is to find the electric field anywhere in space. E, I just argued, has to be 0 inside the conductor. That's really the same analogy in here, okay, because this is an electrostatic condition. E outside, I'm going to create something that does not exist. So I'm at a distance from the center of the sphere R, and this is the radius of the sphere, which is big R. So I'm at a distance R bigger than big R. There, I want to find the electric field. Here is where Gauss's law comes in handy. This is how we're going to apply Gauss's law. We're going to say that this sphere has symmetry. If you're not paying attention to the sphere itself, and if I spin the sphere, let's say, for example, I tell you to close your eyes, since the sphere is symmetrical, I'm going to spin the sphere whichever way I do. For you, when you open your eyes, you would not notice, because it has spherical symmetry. As long as I spin the sphere and keep it its center in its place, of course, I don't move it, I don't give it translation. All I do give it is rotation. Doesn't matter which axis I spin it on, you will not notice if the sphere has the same properties spherically. So that means that it has spherical property. So what I'm going to do in this case, I'm going to use a Gaussian surface that is also a sphere. So this outside surface is called the Gaussian surface, and the Gaussian surface is not real. It's made up surface. Now, we are asked to find, so R itself is specific. It has to be, we can tell how much the electric field inside the sphere is. For R less than R, we have the answer. For R less than R, we know E is equal to 0, correct? But for R greater than R, we want to find what the electric field is. So that's the challenge that we want to do. And for that, what I'm saying in here, we need to invoke Gauss's law. So before we invoke Gauss's law, we have to discover the symmetry of the problem first. The problem in this case, because it's a sphere, solid sphere, we're assuming it's solid sphere, it has symmetry, it's spherical symmetry, meaning that if I spin it one way or the other and you're not paying attention, you would not tell that it was actually rotated. Do you guys understand that? So I want to argue that the electric field now must satisfy also this rotational property. It has to also stay the same if I spin the sphere one way or the other. So the electric field has two options in this case. Okay, it can point, it has to point outside. Okay, I'm assuming that this is a positive charge. If it's a negative charge, it has to point inside. Because let's say, for example, you say, no, I don't like that pointing outside. I want it to point this way, okay? or I want to put it in the other direction other than radial direction. Then when I spin the sphere, okay, when I spin the sphere, you would discover that the sphere has spun because this electric field that was pointing this way in here will basically move with the rotation, and the points will be end symmetrical. You guys understand that? Furthermore, so any other argument, okay, that you argue with this way, I'm going to make a counter argument and make it spin the other way, because all I have to do is spin the sphere in the opposite direction, and then I produce another direction. The only direction that is going to stay intact under symmetry is this direction, okay? That is the direction that is going to stay the same. If I spin the sphere one way or the other, it's going to remain radial. Furthermore, I'm going to argue that the electric field is the same on the entire Gaussian sphere, because R is the same, and since R is the same, and this problem should not change, should not be impacted by rotation. So if the electric field was 10 newtons per coulomb in here, it must be also 10 newtons per coulomb there. So this is the symmetry in this case at work for you. It gives you two things. It gives you the direction of the electric field and the fact that the electric field is the same on the entire surface. So if I am trying to find the flux now of the electric field, it's E times dA. Okay, on that Gaussian surface now. So I'm doing this integral not on any surface. It has to be the Gaussian surface that I have just invented. So the Gaussian surface is not real. We just invented it, this outside surface basically. We just invented it to find the electric field in that point, okay? That's the whole purpose of this. So its properties should not matter really, because it's a made up surface. It's not a real surface. So the properties should not really enter the final answer. And the only property for this surface is its radius in this case, because it's a sphere. But the radius should answer the answer in this case because it's a real property. That is where we want to find the electric field. So R, albeit it's part of the properties of the surface, it's also part of the real problem that we have before us. So the answer may depend on R, but any other introduced properties of the Gaussian surface should not matter. We'll take cases where this is the case. In this case, this Gaussian surface only depends on this real property, which is the radius R. Okay. So the first argument, the patch of surface in here is also radial. So this is where the A points, and that's also where E points. So E and dA both points in the same direction. So the dot product becomes just the product of the two numbers. That's why the symmetry plays a role in this case. So this dot product, the entire surface, the integral on the surface becomes simply EDA, because there is a cosine of 0, and cosine of 0 is 1. Okay? So we use the symmetry already. Furthermore, since we are on a sphere now, the only thing that changes on the sphere is the direction on the sphere of radius R. So R stays the same as long as we are on the sphere. Since we are doing the summation on the sphere, then in this case, the direction only that changes. And E on the entire sphere is the same by symmetry. So E is constant on the sphere. So it's going to come out of the integral. So the only thing that is left for us in terms of finding the flux of the electric field is simply E outside of this integral times the integral of dA. So basically, this is just the surface itself. How big is the surface of this sphere? That's all. And if we consult the books on area of a sphere, so this is the area of a sphere. The area of a sphere, in this case, is 4 pi r squared. Okay? So we actually did not even have to do this integral. Okay? The point in here is, from Gaussian law, you don't want to do this integral at all. So this, per Gauss's law, the flux must also be equal to Q divided by epsilon naught. So now we're ready. So this part in here, we got it from Gauss's law. This is, we just computed the flux, okay, using the symmetry in this case. So at the end, this is the answer. E times the area of the sphere, which is 4 pi r squared, is equal to Q divided by epsilon naught. And from here, we have found the electric field outside of the sphere, or outside of the conducting sphere. So it's again 1 over 4 pi epsilon naught. All I did was divide by this number, 4 pi times epsilon naught times q divided by r squared. This looks like that of a point charge. That's exactly what the point charge also was, okay? Except that's a point charge. This is actually a sphere, okay? A solid sphere of radius big R, but big R in this case is less than little r. So as long as we are outside the sphere, this looks just like a point charge, okay? Historically, this problem was the first problem that was encountered in calculus, actually. And this was Newton, when he discovered his universal law of attraction. He was faced with this problem, and because the apple, when it falls from his hand to the ground, it travels a distance about 2 meters at most. And in his universal law, he has 1 over r squared, and he knew he has to take the distance from the apple to the center of the earth, and to make the comparison between the moon and the apple, in coming up with his basically universal law and coming up with a big value of big G. So basically that's how he was in there. For 4 years, he was trying to answer this question. Why was it that I have to take the radius of the earth and not just any point in here, which is just the surface of the earth at 2 meters in his formula? He ended up basically inventing calculus. That's exactly what happened at that point. That's how calculus was invented, in a sense. So that's what Newton did. But he had already answered all the questions related to Kepler's laws. I explained them and all of that. So the point being in here, that is really the first problem, if you wish, in calculus that was encountered. But the argument for it using Gauss's law is a lot easier, because he ended up doing a lot of integrals, basically, a lot of summations, to be clear. Okay, graphically, this is how the electric field on a sphere would look like, conducting sphere. So this is R. This is the electric field. If I am inside the sphere, the electric field is 0. E is 0 inside the sphere. So the electric field is 0 inside the sphere. So it's 0. This is basically R, the radius of the sphere. Once I am outside of the sphere, it's 1 over distance squared. So if I plug in the value of big R in here, it's going to be a finite value, which is going to be Q over 4 pi epsilon naught over R squared, where R squared is just this radius in here. And it's from there, it's going to drop like 1 over distance squared. So this function is not a continuous function. It's actually discontinuous at the surface of the sphere. It's 0 inside, finite value on the surface itself, and it's going to decrease from there on as you move further and further, like 1 over distance squared, okay? So this is on a conducting sphere. Okay. Again, we're just applying Gauss's law. We're not making anything new in here. No new concepts whatsoever. Problem 22.6. We have a field of uniform line charge. This is a very important example. I want you to really pay attention to it and remind me, okay, around 1, maybe 35 at most. We're going to break down into those problems. We want to see real problems from the end of the book to do how to do them, okay? Around 135 if I go and not talking. So what we have a line charge in this case, lambda, charge per meter. So we have a wire, if you wish. It has charges, how many coulombs per meter, basically. And we want to find the electric field somewhere. Remember, we did this problem already. We did it with the integral. We summed from one side to the other, and we integrated from negative a over 2, I remember, or if I remember correct, to positive a over 2, and then we took the limit when that width of the wire went to infinity. So we found the answer, actually, and the answer, if you guys remember, dropped like 1 over distance squared. So I'm going to use this distance being r again. How far are we from the wire? So that is a real number, so that should matter at the end. So and I think it was lambda over 2 pi times the distance. So epsilon naught, I'm sorry. This is how much the electric field was, okay? So it dropped like 1 over distance squared, 1 over distance, I'm sorry. So the question was, we did an integral. You can do it that way, but now we're going to use Gauss's law. So for that, we're going to invent. This problem has a cylindrical symmetry, because again, if I spin this wire one way or the other, you would not tell also But as long as I just spin it around its axis, this has a finite radius, of course. So if I spin it around that axis, you would not notice, okay, if you're not paying attention that this wire has spun. Furthermore, if I rotate it also from one end to the other, you would not have noticed it also. As long as you're not paying attention, I take the infinite wire and flip it around, you would not have noticed that this thing in here. Also, if I can move it in or out, you would not have noticed. Remember, this is an infinite wire. So if I bring it 1 meter away from where it was, it's an infinite. So both sides are going to be the same. So making this argument, the electric field in here must also be pointing outward. I'm assuming lambda is positive. If lambda is negative, I'm going to have it pointing inward. Okay? Because again, if the electric field is different from point to point, you would notice that. What I'm saying in here is the entire electric field, a distance r from the wire, must be the same. Because if this was 5 and this was 10, and if I move the wire slightly, you would notice. You would notice that the value that was 10 now has shrunk a little, okay, or changed. The only way this can be then is that the electric field must be the same everywhere at a distance r from it. And it's the same actually on the anywhere in here too. Because again, if I spin it a distance r, you should not notice. So whatever value was there, well, if I spin it enough, it's going to be there. So the value of the electric field at a distance r from it, it's the same. Okay, that's the argument. So this has to be pointing by symmetry upward, I mean away from the wire if you wish. And this is on a let's come in here and look at it from one side or the other, doesn't matter. So I'm gonna come in here and see this wire, okay? So that's my vantage point now. It looks different from that vantage point. This is the point. Remember, this is extending toward infinity. And at a distance r, the electric field will be pointing like this, like a hedgehog, okay? But it's the same magnitude, okay? Okay, it's the same magnitude, whatever that is. So again, I'm looking at it from that point. Let's keep on focus on this one. So my Gaussian surface in this case is going to be a cylinder of length L. So I introduced something in here, length L. This is not part of the real problem. So the answer should not depend on L, because if it does, we have a disaster before our hand. Because if I bring another Gaussian surface that is not the different length, I will have a different answer, and that should not matter. We just argued that the answer depends only on R. It should only depend on how far we are from the wire. Having said that, let's now, this is the Gaussian surface. It has two bases. This is base 1. It has another base on the other side, base 2. And it has this lateral surface, the side surface, okay? So we have 3 sides to it. We have the lateral surface. If you come and cut this whole surface is not really a surface, by the way. It's just a made-up surface, a mathematical surface. Since it's a mathematical surface, I can cut it anywhere and open it. So if I open the surface, this length is L, but this circumference is 2 pi times r, because this distance is r. I'm sorry, this distance is little r. So this circumference is 2 pi r. So it looks like, if I open this lateral surface, this is how it looks like. The length is L, and this side is 2 pi r. Okay? So its area is simply length times width. So the area of this surface is 2 pi r times L. Remember, I don't want to do any integrations. I want just to use basic geometry to solve my problems. So I'm going to find by symmetry now the electric field points this way. And this area points this way. So the base 1 points at a 90-degree angle from the area. So the dot product of this surface will give me 0. So let's break down the integral now, because we have 3 integrals that we have to do for the surface. So the flux again of the electric field must be equal to the sum on closed surface of EDA. This sum, I'm going to break it down on surface 1, B1 basically, times dA, plus I'm going to do the integral now on B2, which is the other area. The electric field is pointing this way, and the surface area is pointing there. So that's also negative 90 degrees, because this is from EDA, that is actually negative 90 degrees. This is where the negative, if you want to call it, BA, or doesn't matter. It's cosine of 90 degrees or negative 90 degrees is 0. So both of them should give me 0 because of that dot product. Plus the integral on B2 times EDA. And finally, on the lateral surface, that is where the whole thing is going to happen, actually. That is the non-zero contribution, plus the integral on the lateral surface of EDA. So that is basically the whole thing. Now, again, this is 0 because E and the area are perpendicular. That is because E and the area are perpendicular to one another. This is also 0 for the same reason. E and the area are perpendicular. This is not 0 though, because E is the same on the entire lateral surface. I just argued that because this is how the electric field would look like. It's the same value, and the area is this is where the area is. I'm sorry, why it's not right? Oh, because it's turned off. This is where the area is. So the area is pointing in the same, or the patch of the area, if you like, and the electric field are pointing in the same direction. So there is a cosine of 0 now between them. And the electric field is the same value throughout the entire lateral surface because of the symmetry. So I'm going to, first of all, make the dot product into just simply E times dA times cosine of 0, which is 1. And then take E outside of the integral. So at the end, this whole integral boils down to E times the area. And the area, I just argued, is 2 pi r times L. This is the flux of the electric field. And it's clearly, it depends on L. And that is disaster. That is no good. We have to really get rid of that R, L. The flux may depend on L, but the electric field should not, okay? Let's find the charge enclosed divided by epsilon naught. The charge enclosed is in this area only. This is how much charge we have. We took an L length and we have lambda coulombs per length. So in this case, the charge enclosed should be lambda times the length. So that's it, because we took only the charge enclosed. We don't care about the other sides. We don't care. Don't tell me, okay, how about this outside of the cylinder? That is not enclosed. What we matters in here is the enclosed only by this Gaussian surface. And what is enclosed is only the L part of the wire. So in this case, the charge enclosed should be lambda times L. Plug in there, and we will have the value for the electric field. So 2 pi r times L should be the charge enclosed, which is lambda times L, and divided by epsilon naught. This is where the L cancels. We don't want L to be part of the answer because L is made up. L is a fictitious thing. We just made it up to help us solve the problem. We took a length L of the cylinder, which is just an arbitrary length, okay? So at the end, the answer should not matter. And the answer, of course, is E is equal, again, to lambda over 2 pi times epsilon naught times R, as we have found last time when we did it with the integral, okay? Probably we didn't use the letter R, we used the letter Y, but it doesn't matter, that's just how far we are from the wire, okay? So that's the answer we found last time doing the integral, okay? See the other examples quickly here. So this is important, we just covered it, of an infinite plane. So I'm gonna do this quickly and then go into jump into the examples. Okay. The two plates, once we find it for a plane, the two plates is just basically, like I said last time, it's to trap the electric field. Should be an easy application for it, okay? This example is very interesting. I really want you to go and look at it too, because it's a practical example. You want to know how many charges there are when you walk on the ground, you're actually touching with your feet, okay? And then the field of a uniformly charged sphere, that is a non-conducting sphere. It's similar to the problem we did so far, the initial problem with the conducting sphere, except now you don't have a conducting sphere, it's an insulating sphere. So there could be and there will be an electric field inside the sphere. And the curve for that part should look a little different than this one. Actually, it's going to look like this for a non-conducting. So it's going to increase linearly and then it's going to drop. So this curve is for this part. it's for this example, okay? So that's not, so that's an insulating sphere, okay, not a conducting sphere. So the curve will, the electric field will increase really linearly and then drops like 1 over distance squared, just like it does also for the conducting sphere. But inside it's not zero, it grows with distance, okay? There was another example that I want to, yeah, have a question in here? Yes, inside the non-conducting sphere, inside the insulating sphere, you have, because of the symmetry, you have to take a sphere also. But its radius, of course, has to be less than that of the big sphere, which means that when you do the calculation, and that's really where the things cancel a little bit. Okay, let's talk about that example quickly and take advantage of what we did so far. So here is a non-conducting sphere, and I am inside now, okay? And I have a rho charge per unit charge, so per unit volume, I'm sorry. So in this case, I have rho times the unit volume. The unit volume is 4 pi r squared dr, okay? That is the unit volume inside the, where you still have spherical symmetry. So in this case, rho 4 pi r squared dr integrated over this volume, it's going to give you rho times 4 pi over 3 r cubed. So this is how much charge is enclosed. This is how much actually charge in here. This part does not contribute because it's outside of the Gaussian surface. And this, divided by, of course, epsilon naught, must be equal to the same value as we did, 4 pi times r squared. This r squared and r cubed drop, cancel, and you'll be left with r in here. That's why there is that linear growth inside the sphere, okay? But outside of the sphere, there is, this value will be fixed because you integrate the charge enclosed, and the charge enclosed is only here up to big R. So there is no r cubed in here. There's a big r cubed, but that's a constant number. Divided by r squared, that's why it drops like 1 over r squared. Drops like 1 over this distance squared, okay? So that's really how this example works. I suggest strongly that you go through it. And if you have difficulty with it, please let me know, because this is critical for your exam stuff. You have to understand how to do this part of the integration, okay? This is because rho is constant. If rho is not constant, I really have to do this integral. If rho, this is a lot of your homework problems. Rho dv over from 0 to big R, I have to actually do this integral. Rho, in this case, is not constant. It's some function of R, okay? I still have that symmetry. And dv is 4 pi r squared dr, okay? So, and there is a function here, so I have to really do the integral. The only reason was I was to do it quickly in here in this example, also from that example, is because rho is constant. So I'm left with 4 pi r squared dr, which is r cubed over 3, okay? From 0 to r, so it's easy, okay? But if rho, and there's a lot of homework problems where rho is not constant, it's a non-uniform distribution of charge, but it still has that symmetric, spherical symmetry, so it only depends on r. So as it grows or shrinks, it grows in the entire sphere or shrinks the entire sphere. So it still have that symmetry. So you can still take advantage of that symmetry to do the Gaussian surface and to do the Gauss's law. But you cannot take it out of the integral because now it's a fixed number, okay? It's some number, okay? Which brings me to the examples that I gave you in here. So let me first of all see the other examples from the textbook and see which one might give you a headache in here. The flux through a cube. No, this is, we did that last time, sorry. Okay, field of a uniformly charged sphere. So we just talked about that. The plates, okay. Let's do quickly the plates and then we'll go through the examples that I posted for you guys. Okay, I have an infinite plate in here. Okay, and it has the sigma charge per unit area. And I want to find the electric field somewhere, okay. A distance, it doesn't matter, R or Z, we're gonna call it whatever, okay. Z, for example. It doesn't matter what shape I'm going to take in here. So I'm going to take, for example, a circle of radius A at a distance Z and go and project that circle and go to the other side by symmetry, the same distance Z from it. And I have a cylinder now with two bases. Base on the top, base on the bottom, and also I have the lateral surface. But by symmetry, the electric field must be pointing outward again, and it's the same as long as I am on the same distance Z. So on the same surface, the top one or the bottom one, I have the same electric field in magnitude. Now, again, because if I move it one way or the other, you wouldn't tell, so it has to be pointing outward, and the magnitude is the same, because if I move it one way or the other. See, the symmetry argument now here is very helpful. But on this lateral surface now, the surface points this way, and the electric field must be pointing upward or downward, doesn't matter. So in this case, there is a 90-degree angle between them. So in this case, it's opposite to what the wire was. The lateral surface will give me 0 contribution to the flux, but it's the basis that gives me some value. And the base is, in this case, just the electric field times area, E times the area. Remember, the area, I took it arbitrary. It can be any shape. I took it as a circle, but it doesn't have to be. It can be any shape you like. So I'm just multiplying by its value, okay? But that's an introduced property. That depends on my choice of the Gaussian surface. So the answer should not matter in this case. So you ask, it's supposed to be the charge enclosed divided by epsilon naught. How much charge is enclosed? So this is the projection of that surface on this side. Remember, I have sigma charge per area. Since I have A area, which is any arbitrary area, therefore I have sigma times A. And this is where that introduced property should cancel out. And did I make a mistake in here? I'm sorry, I have one side. So the top side will give me this much, and the bottom side, because the area is pointing outward and the electric field is pointing outward, in the bottom area, the electric field is pointing downward, and the area also is pointing downward. So there is another side also from the bottom, which is EA. So both of them will contribute the same magnitude. At the end, the answer, when A drops from both sides, is going to be E, which is equal sigma over 2 epsilon naught, a result that we found also with the integration. It did not depend on Z either, like last time also when we did with the integration too. It does not depend on how far you are from the surface for the infinite plate. So this is in a nutshell also another quick way of finding the same answer we did, and it took us a little bit of work, honestly, to do it with the integral. This one is quicker, because again, the contribution, I mean, let's be specific in here. Let's add 0 to it to say that it has to be closed surface, except we know the lateral surface in this case by symmetry will give me 0 contribution, okay? Which brings me to, unless you guys have a question about these things, to the 2 examples I gave you on Canvas. You ready for them? Okay, so you have to really follow the steps in how to solve problems, because this is from toward the end of the book, actually from the newest edition. So you have to really follow how to do this thing step by step, because we really have to understand this thing. Here, how they look like on Canvas, okay? Again, problem 20, from chapter 22, problem 59 and problem 61, okay? The 15th edition, just to make sure that you guys are aware of that. So if you have access to the book, that is how, when I asked the publisher, this is what they sent me. They sent me the 15th edition now, because they don't have the 14th edition available. Anyway, a very long insulating cylinder with radius R cylinder. The first step in solving any problem in physics is you have to read it first and understand what the problem was asking and get the information out and see what is you're asked from. This is step 1. You will be graded on it, okay? You will lose points if you don't do this step, okay? So a very long insulating cylinder with radius R cylinder has a non-uniform positive. You see, this is not a uniform charge. This is not like what I did earlier where you take a rho outside of the integral and I'm done with it. No, this rho depends on how far you are from the center of the cylinder. So this rho matters now. Has a non-uniform positive charge. It's positive, they tell us, of density rho equals to, this is how it depends on how far you are from the center. So it depends only on how far you are from the central axis of the cylinder, okay? Well, rho naught is positive, I mean, is constant, and R is measured radially from the axis of the cylinder. Now, a particle of charge negative Q and mass big M orbits the cylinder at constant distance. What is the linear charge density lambda of the tube in terms of R cylinder and rho naught? So they want to have the lambda, basically, the charge per unit length on the cylinder itself. And then they ask to determine the period of motion, T, the period T from physics 1. Remember when an object is going spinning, it has a period. It goes every so many seconds once around its center of rotation, okay? So we want to find that time, t, in seconds, okay? And use Gauss's law to determine the electric field and therefore the electric force felt by the particle that acts centripetally. Okay, so let me grab my notes in here and see if we can solve this problem together. I'm going to stop sharing that screen. And I suggest that you guys start writing at this point the solution, because I want you to really have a feel of how this thing says. So if you don't have that screen open, I suggest also you open the problem too, so that you have a look at it too while we are doing this problem. So the first part, it says that I have a cylinder of a radius r cylinder. So this is what I'm given. What is my writing pen? Okay. So the radius of the cylinder is r cylinder. This is one piece of information. Rho, which is the distribution of charge, and they're specifically saying it's non-uniform. I know it's not uniform because of the fact that it depends on r. So rho is equal to rho naught times 1 minus r over r cylinder. So that was given to me, okay? So if I were to imagine this, when r is equal to 0, this value of rho is rho naught. So in the center, there is a rho naught charge. As I move along from the center of the cylinder toward the edge of the cylinder, where r is equal to big R cylinder, 1 minus 1 is 0, so there is no charge. So I start from rho naught per unit volume, basically Coulomb per unit volume, and then it starts to drop until it gets to 0. So this function, this is how it looks like. This is just rho, not anything else, not charge even, okay? So this is rho as a function of distance, so it's some finite value, which is rho naught, and it drops until it becomes 0, where r is equal to r cylinder, okay? So I'm trying to analyze a problem, and in the same time trying to find a way of also solving it. So I'm just looking at what was given to me. And then it says that, now what they did, let me draw this problem in here, and this is part of the solution, by the way. Now let's visualize this problem with a graphic, okay? So again, this is all part of step 1. So here is how the cylinder looks like, okay? It's a big cylinder, very long cylinder, okay? Because we're asked at some point, so this is an infinite cylinder at this point. So this is the radius r cylinder that we're talking about all along. And the charge depends only on r, where r is the distance from the center. At some point in here, called r or orbit, we have a negative charge of negative Coulomb, negative q, and of mass m, okay? So that's what was given to us. And it's spinning, okay? It's going around in a circular path around this thing. Because if it doesn't spin, this is a positive charge, and this is a negative charge is going to smash into it. But it has to move fast to stay in orbit. So that's basically what we learned from physics 1, okay? So that's what we want to apply in this case. So that's what was given to us. What do we know? That's the second step. We know that Gauss's law, first of all, that's what we're going to apply at some point. Electric field, I'm sorry, Control Z, what am I doing in here? The flux of the electric field is equal to the charge enclosed over epsilon naught. And we want to find the electric field here. Okay, at a distance r greater than r cylinder. So we want to find that. That's really how we have to do it. So that we have to find. If we don't find that, we are not in business. But they want us also to, they asked us, and this is part of the step 1, I'm sorry to find it, lambda, and they asked us to find t. This is step 1, okay? That's what we want to, we were asked to find, okay? Now, so this is what we know so far. We also know Newton's laws of motion, and Newton's law of motion says F equals to ma. And F in this case is Q times E. That's why we need to find E, as a matter of fact. We need to find the electric field there using Gauss's law. In this case, Q is actually negative Q, so it's going to be big Q, okay? Q times E. I'm going to just use it without signs because I know the electric field must be pointing inward because this is a positive charge and this is a negative charge, so the electric field is toward the center, and this is a centripetal motion. This is equal to mv squared over r, or equal to m omega squared times r orbit. Okay, you guys remember this law from physics 1, which is also mv squared, and m is actually big M too, which is big M times v squared over r. Do you remember this law in a centripetal motion? It's ma really, and the a is centripetal acceleration, that's all. Yes, do you guys remember this formula from physics 4a? I need a feedback in here. Yes, no? Okay. Okay, basically, when you guys did physics 4a, we're still using F equals to ma, really. Okay, that's all we're saying in here. F equals to ma. And we have to find F from this problem. And A, in this case, is centripetal acceleration. And the centripetal acceleration, when you do the circular motion, there are two kinds of accelerations. There is the acceleration along the radial direction, along the, the path of basically, which is the circular path. The tangential acceleration, I remember the word that you guys used there, the tangential acceleration and the normal acceleration. Well, the tangential acceleration, this is a uniform motion, so there is no acceleration along that side. So it's only the normal acceleration, and the normal acceleration, whenever you have a circular motion, and we will come to this expression again and again in this class, with the cyclotron and with different kinds of accelerators, is v squared over the radius, okay? And we have a centripetal acceleration here, or normal acceleration. Does this ring a better bell now? Does this ring a little bell a little? The normal acceleration when you did the circular motion. Okay, good. At least a few people now remember it. Okay, very good. So now we're in business. So F in this case is Q times E, and it's toward the center, it's central force. Q times E. And another expression also for the centripetal acceleration is omega squared times r, okay? Because V is equal to omega r, okay? Except that we're sitting at the orbit in here. So it's going to be the mass of the particle times the omega squared times the radius, in this case, of the orbit. So this is the expression that we want to find. There is another relationship that you guys must have known also, which is omega is related to the period via this expression, 2 pi over t. Does also this one ring a bell from the central, from the physics 4a? Omega is equal to 2 pi over t. You guys remember that expression too? Okay, very good. So we need that result too in here, because we want to find t. That's the question they want us to find, okay? So that's basically what we want to do. So we have to find t. That was a question that we really needed to answer. So this is part of the question that we need to answer. And the other part that we need to answer is, what was the first question in here? Because if we don't keep track of the questions, lambda. Lambda is not a wavelength. Lambda is just a charge per unit length. Okay, so let's find lambda first, okay? I'm going to take a part of the volume. So I'm going to redraw. We're solving now, okay? We're going to take, this is a big cylinder now, and I'm sorry, we don't have a big real estate in here. So, and I'm going a distance inside of that cylinder, at the distance r from it, okay? I'm going to go around it in a circle. So this side in here is 2 pi r. That's the circumference of a circle of radius r, okay? If I go a distance away from it by dr, this is how much area I am enclosing. So this is the strip I'm taking from this shape. So this is dr, okay? Furthermore, I'm going to move a distance dz. So let me draw this patch closely, okay? So this is how it looks like. It has a width of dr, a length of 2 pi r, and a height of dz, okay? So it's a thick element of that entire cylinder. This is not the entire cylinder. So 2 pi r, that's the circumference, times dr, that gives me just this area, times dz, give me the entire volume. If you did cylindrical coordinates, that's basically the volume where theta is already integrated, okay? So basically, This is, when I open it, this is how it looks like. The length in here is 2 pi r. The height in here is dz. And the width in here is dr. Okay? So I'm moving dr from the center. So r is 0 and exceeding this one. Does everybody understand that this is the element of the volume? In this patch that I just created? And this, not patch, this is part of the cylinder, not the whole patch. This is not an area, this is a whole thing, okay? This is the volume itself. Because I want to find the charge enclosed in this element in here. Of course, this is expanding 2 pi r. This is going through the entire radius. But when I open it, it doesn't matter. It looks like it's a big, basically a piece of wood, if you wish, okay? So the charge in this case, dq, must be equal to rho times this dv, okay? That's how much charge you have in there. So, and dv, I just found it in terms of everything I know, which is 2 pi times r. Rho is not constant, that's the problem with it. Times rho times dr times dz. And since I don't care for the, I'm going to sum from r equals to 0 to big R, okay? To the r of the cylinder. So I'm going to sum from r equal to 0. I'm going to not deal with the dz integration because we're not going to need it at all. So the only thing that we're going, so we're going to start from the center where r is equal to 0. Remember, that's where the most of the charge is concentrated. And we're moving away toward the edge where r is equal to r cylinder, okay? So we're going to sum through all of that cylinder, and then the dz, we're going to leave it finite because that's going to help us find lambda, okay? I mean, not finite, infinitesimal, I should say, okay? So in this case, the charge enclosed on just that element is going to be summation from 0 to big R cylinder of this entire expression, 2 pi r. dz is going to come out because it has nothing to do with this integration. 2 pi r times rho times dr, okay? dz and dq is exactly what lambda is. So lambda is the charge per unit length. And since I already took a finite length, so I'm going to say dq over dz is exactly what I'm looking for. So this is the integral I have to do. So this integral is from 0 to big R cylinder of 2 pi times r times rho, which is a function of r, by the way, times dr, okay? And now we're in business. So that's how lambda I defined it. Because I took dz, which is a certain height, an infinitesimal height. But if I took a very long height, 1 meter, for example, that's going to be lambda times that 1 meter. Since there is that symmetry, it doesn't depend on z, the rho itself depends on r. So I'm going to assume this is the linear charge. The charge per unit length is the amount of charge on that length L, of length L divided by that same length L. Except I didn't take an L length, I took a dz length. So I have a dq charge, okay? So at the end, this is basically how much it is. So lambda then is going to be equal to 2 pi is going to be part outside of the integral. The integral from 0 to big R cylinder, RCY, R times rho naught. Rho naught is constant. That's what they said in the problem. So I'm taking it out. Times 1 minus R over R cylinder dr. And this is a simple integral. R times 1 is R. When I integrate, it's going to give me R squared over 2. And R times R is R squared. When I integrate, it's going to be R cubed over 3. And don't forget, I have already an R in the denominator in that expression. So this is how lambda look like then when I actually do the integral. 2 pi times, what is it? 2 pi times rho naught times R squared over 2 minus R cubed over 3 times R cylinder evaluated between 0 and R cylinder, okay? Well, this one is going to give me R cylinder squared over 2, and this is going to give me R cylinder squared over R cylinder cubed over R cylinder. Cancel one of the R cylinders, and you will be also left with R cylinder squared over 3, okay? And you will have 1/2 minus 1/3, which is 1/6, and the expression which should be 1/6 cancels the 2, so it should be pi times rho times r cylinder squared over 3. So that's the answer for lambda. Okay. I suggest you do these steps by yourselves, okay, because it's critical that you know how to do these things. Again, it's helpful for you for the exams because a lot of these questions are similar to that. Even in the homework, they're similar to these things, and you have to learn how to do this kind of integrations. Most of the times when calculating charges is going to be some power law, something to the power of something, okay? Either the 1, 2, or 3, or cube, or something like that. Yes, you have to be, you have homework on Pearson, but some of the homework, Omar is asking about the Pearson code, yeah, for the, because we have two kinds of homework in this class. We have the mastering physics homework and also this submittal, the ones that you're supposed to be doing. This is not part of the homework, by the way. This is just a class work, okay? That's why I'm proposing to solve this guys for you guys. Where, Daniel, where do you want to go back? Okay, like I said, Daniel, I would recommend that you guys follow these things, go back to the notes. I mean, when you come back to the video, watch it again and make sure you have a full grasp of these things, okay? The piece that is really a problem is here, okay? Once you set up the problem correctly, that's it. Once you set up the problem right, and this is true for any problems of this type, okay? This is true for, yes, that's probably what I suspected, that needs a little bit of focus. dq is equal to rho, remember this is this dq, the entire volume. It's rho times dv. So what I did in here, I broke down this dv into two elements. The dr part of it, actually there were three elements in it. The d phi already was done, which is 2 pi. Okay, since I took 2 pi times, I took a whole ring, if you wish, first, okay? And then I took that ring of length of height, basically, of certain finite height. So this became a real object, okay? So now a ring, and then with a height dz. Since the height dz now, I will have dq on it only. I don't have the entire charge of the cylinder. If I know the length and the height of the cylinder, then I can integrate from the one boundary to the other boundary of the cylinder. But I took a dz part of it, and then divide that dq that I find just for that entire surface divided by dz. That's what I have defined as being the lambda, in this case, charge per unit length. Let's check the units. This is coulombs per meters cubed. That's what the energy, that's what the charge density is. It's coulombs per meter cubed times meter squared. So I'm really dealing with a coulomb per meter, okay? So I have the proper units for it. Always, when you solve problems, make sure first that the dimensional analysis works, okay? So this is step one. This is not the entire solution to the problem, though. This is just finding lambda. Remember, we have two questions, finding lambda and then finding t, the period t. Now, in order to find the period t, now we're going to invoke this law. First, what is the electric field? We just found it for a wire, okay? We're going to use that result. If you don't like it, you can use Gauss's law. And Gauss's law says, basically, the charge enclosed. So we're going to take an imaginary made-up surface around this cylinder. Let's take this cylinder in here. Let's take a different color, okay? Let's take the green color now. So here is the cylinder. If I turn on this thing in here, here is my cylinder now. So this is an imaginary cylinder that has the same radius, which is important, but the height in here is L, okay? And apply Gauss's law to it. Gauss's law says in this case, again, by symmetry, the electric field must be pointing either inward or outward. In this case, it's going to be pointing inward because, again, excuse me, again, the charges have different signs. So the electric field must be pointing inward, and it cannot be pointing at an angle or the other, because if they move this one, you will discover that, and it's the same value everywhere. On this side, though, the electric field is pointing inward, and the area is pointing outward. So this will contribute 0 flux. The bottom area also will contribute 0 flux. It's the lateral area only that matters when I do the flux. So again, using Gauss's law in this situation, should give me E times the lateral surface. The lateral surface is just like the other surface that we did earlier, which is 2 pi times the r, which is how far we are. And r, by the way, is r orbit. okay? Because we are at a certain point now. 2 pi r orbit times the length L I took from it must be times, this is the area, times E. That's the flux. There is no vector on this one in here, okay? Oh man, my computer is slow to respond now. Okay, times E is equal to the charge enclosed. The charge enclosed is lambda times L divided by epsilon naught. Cancel the L. Erwin in business. Now, the electric field, we know its value. The electric field E, in this case, is going to be equal to lambda divided by 2 pi epsilon naught times r orbit. Okay, so as long as we are on that orbit, because the charge is supposed to be on that orbit. So it's lambda divided by 4 pi epsilon naught times r orbit. Okay, remember we found the value of lambda, which is pi times rho times r cylinder over 3 and r cylinder squared. So we really needed to express the electric field at some point with all what we know. Okay, and what we know, what was given in the problem is rho, r cylinder, r orbit, and that's it. I'm sorry, rho, this is rho naught, okay? This expression is wrong. This is not rho, this is rho naught. It's this number. Okay, you have to fix that. Okay, so this is rho naught. Okay, so that's what was given to us in the problem. So we should be able to express the answer in terms of that. I know we have about, how much time we have left? 5 minutes or 10 minutes? 10 minutes, so we should be in good shape to finish this thing. So we have the electric field now, and we're going to invoke Newton's laws of motion, the second law of motion, basically F equals to ma, knowing what A is. So we're going to express this one, Q times E, and we just found E. Q, which is the charge that is spinning, times E, which is lambda over 4 pi epsilon naught times r orbit, equals to the mass times omega squared, which is going to be 4 pi squared over t squared times r orbit. Or is it times r orbit? Yes, times r orbit. Remember from this expression that I put in there what we know? Yes, r orbit, okay? Because we are on the orbit, that's the distance we are from the center, okay? Okay, so now, from here, we're going to find what the t is. So move things around, move q around, and things like that. You should find the expression for what t is. So I'm going to rewrite the expression here. T squared is going to be equal to mass times 416, that is, pi cubed times, I'm going to deal with the r squared later on, divided by q times lambda, and lambda we found an expression for it. Lambda we found to be equal to pi times rho naught, pi times rho naught, and then I have also an r squared in there, times 3, by the way, times 3 in the numerator. And what else do we need in here? I'm sorry. And you have an r squared in here, and the other r squared. That's why I left this r squared. R orbit over r cylinder, the whole thing squared, okay? And take your square root and get rid of this pi in here. You'll be left with a squared in here. So get rid of all of that, and basically you have something in here to check your, oh, there is an epsilon naught I'm missing somewhere in here from this expression. 4 pi epsilon, there is an epsilon naught in here. Don't forget the epsilon naught, okay? It's important. So, at the end, take the square root and find the expression for t. You need to check that this dimensionally makes sense, because this has to be at the end the second squared, and this must also be a second squared, okay? Don't forget the unit for the mass is kilogram, the unit for the Q, which is coulomb, the unit for the charge per unit volume, which is coulomb per cubic meter. This they cancel. There is no units for these numbers. The pi have no units, but the epsilon naught definitely has a unit. And the unit for epsilon naught is equal to what? Coulomb squared divided by Newton times meter squared. So plug in all of those numbers and everything should cancel properly. And don't forget the Newton also has a kilogram times meter per second squared. So everything should work out to give you at the end of the day the proper units that you have to do, okay? The Newton is coming from epsilon naught. The units for epsilon naught, just to make sure that you guys are aware of it, epsilon naught is a Coulomb squared divided by Newton times meter squared. Okay, you need those units to check your answer. So, and here in the denominator for epsilon naught, there is a Newton, and Newton has a kilogram to cancel that kilogram, and times meter divided by second squared. Okay, and the second squared will go upstairs, exactly what the doctor ordered in terms of your units. Okay, I promise that if you guys, any questions about this problem? It's a long problem, isn't it? It's a fun problem. Here is the deal. If you don't do it by yourself, you're not going to learn a lot. So the problem is on canvas, and you really have to learn how to do that problem. This is not as bad as the second problem, honestly. The second problem is even nastier a little bit because it involves a little bit more geometry than this. Okay, yes, you have to do that. And do not, I'm going to publish a solution for you guys, but for both of these problems, including the second problem also, but do not rely on, because if I do it, it's going to be basically concise, just like what you see things. You have still to go through the steps yourself, and you have to really sweat through these things and get some things and understand what's going on. Let me go to the second problem though, to try to see how that works. Okay, at least set it up. Okay, I know we still have about 4 minutes left. So it says in here, a uniformly charged insulating sphere with radius r. So the radius of the sphere is little r. And charge positive q lies at the center of a thin-walled hollow cylinder with radius big R, bigger than little r. So imagine the following. You have a sphere of radius little r, and it's inside a big cylinder, okay? And the cylinder has length L that is bigger than the 2r, bigger than the diameter of the sphere. So in other words, the sphere is sitting inside comfortably of the cylinder of radius big R, which is bigger than the other radius. So even on this side, it sits comfortably, and also on the other side, it sits comfortably inside the cylinder. So the cylinder has properties where it encloses the entire sphere, okay? The cylinder is a non-conducting and carries no net charge. So the cylinder has no charge on it. So the cylinder has no problem. And it's hollow. So it's not, the charges are not going to be inside because the entire thing is hollow, okay? The question is, determine the outward electric flux through the rounded side of the cylinder, executing the following end caps. So basically, the first question is actually just set up for the second one, okay? It probably should not be a question at all. It's the determine the electric flux upward through the, no, the rounded side. I'm sorry, that's a question, okay? That's what you, the rounded side is what I call the lateral side of the cylinder. So we're gonna calculate the flux through the lateral side. Here is where the difficulty with that problem is. Let me go back, stop sharing this screen, and illustrate to you where the geometry gets complicated and where you really need to get into the secants and functions like that. Okay, let me get out and come back in. Okay. So here is the setup for this problem. We have a sphere, and the sphere is inside a big cylinder, and the cylinder is hollow, okay? The sphere, of course, will produce electric field that is radial. So in this point in here, here is where the electric field in there. But in this point, here is where the electric field is. And in here, here is where the electric field is. So if I'm trying to find the flux of the electric field, I'm sorry, am I not sharing my screen? I was not, sorry. So again, here is the sphere inside my big cylinder, and the electric field at some point, it's in the same direction as the area. But in here, the area is pointing this way, and the electric field is making an angle with it. And you have to integrate from negative L over 2, because they tell you they put it in the center, to positive L over 2. So instead of doing that integration, I'm going to integrate with respect to this angle in here, theta. And the angle theta is going to vary from finite value to another finite value, because the length L is finite. It's not an infinite angle, infinite length. So in this case, the integration becomes complicated because it involves this cosine of theta, and the integration in here, this patch in here, would depend on how far you are, because this length in here depends on how far you are on the z-axis. So if this is z, this depends on z, so this will become square root of this radius, which they tell you the radius of the cylinder itself, r squared plus z squared. Okay, and you have to do this integration with respect to z or with respect to theta after you do change of variable. Okay, so don't forget to change the boundaries of integration also when you do the with respect to the angle too. Okay, so this is basically the complication. Same thing true also when you do the second part, which asks you to find the, if it is this area, this side of the area, the electric field and the area, they point in the same direction. But any other side, as you move along in the radial direction, now you have a problem, because the area points this way and the electric field points at an angle. Same thing, you have to deal with that angle there too. And the same thing in the bottom. And when you add them up, you add them up. So the last step of the problem is kind of easy a little bit, because the hardest problem is finding the first two steps, and then the last part of the problem is just adding the two. Show that the resultant is consistent with Gauss's law, and that is when you check actually to see, calculate the charge enclosed divided by epsilon naught, and see if there is a match. It should really be the same number. It should be Q divided by epsilon naught, because that's the Q in here that you're dealing with. The charge, basically the electric field outside of area is just Q over 4 pi epsilon naught divided by the distance squared. But the distance now matters. That's the problem with this problem. The distance depends on, because as you move along the cylinder, it's not a spherical symmetry now. You're going along the cylinder, so the distance changes on how high or low you are from the cylinder. Okay. You guys have an idea of how this one also is going to come out? The key thing is that distance and how it depends on z, which is 1 over square root of r squared plus z squared. And you integrate from negative L over 2 to positive L over 2. Okay, for z, that is. You sum up, because you're going to find the flux on a surface, which is the sum on that lateral surface, that's all. Okay. Try to play with these problems. Do not forget you have a bunch of homework also, that is, please do not exceed the deadline, and so that you have your work submitted. It's better to get a grade than no grade whatsoever. And I give also partial credits, so do that too. So you're going to get partial credits for showing your work and trying to show that you're doing that. About the homework. Yes, it's through. The question was about the Pearson learning. It's mastering physics. It's through. There is a link actually on Canvas. Okay, where you need to go. Okay, you need those ones too. I think the deadlines are approaching next week or something for the homework too. Both homeworks are due next week. All homework actually is due next week. There will be more homework for chapter 23, which we did not start yet. It should be available by Monday or Tuesday at worst. Chapter 23. Okay. Okay, if you can't access it because the code is probably the one you bought it for 15th edition, talk to the publisher. Okay, talk to the publisher. They should be accommodating. Okay, contact them immediately. They will change the code for you to work. Yeah, contact the publisher, please, okay? Make sure it works for you. Because I've had this experience in the past, and if the publisher doesn't get in touch with you, I'm going to get in touch with them. Please let me know so that we can get them to give you access. Anybody else? I know there are several of you already are in mastering physics, but anybody else is experiencing problems connecting with the code?
Yeah, so I'm registered in the class, and I purchased the class already, but for some reason, it's saying that I'm signed out all the time.
Oh, signed out. Okay,
yeah,
can you try
like
to?
On the home page, it says I can't access any of the assignments or anything. It just says I'm signed out. That's all it says on the screen.
Okay, can you contact the technical support also for that?
Okay.
Okay, I will try to see what's going on. I think the only reason why I did the 14th edition is because you guys used the 14th edition in the past. Probably the instructor there did not require you to do mastering physics, but if you bought the book, it had the code also with it too.
Does it matter that I used my personal email because I had made an account from chemistry last semester?
If you are successful in chemistry, it should be successful also in this class too. I'm
Okay,
not requiring student IDs. I'm requiring them through basically your. Okay.
Okay, thank you.
Mm-hmm. Okay, guys. See you. I guess Wednesday because there is no class on Monday because of the holiday. And enjoy your holiday.
Professor.
Yes.
So on the canvas, like
Mhm.
chapter 21 homework, we do that by hand and we do the mastering physics? Okay.
Both.
Just making sure.
Yeah. Yeah, the hand you submitted online, you submitted on Canvas.
Yep.
And the one on mastering physics, you just go there into mastering physics, okay?
Gotcha. All right, thank you.
Okay, no problem. Okay, I'll try to probably change the due date for the mastering physics to make sure everybody is on board with that and fix all of the technical issues. But there should not be any delays for the ones they submit by hand, okay? The ones that needs to go on Canvas. Does this make sense to you guys so that you work out whatever technical issues you have with the... Okay. No problem. So I'm going to extend it for another week after the deadline to give you time so that you fix all of the issues that you have with the vendor, the person. Okay? Okay, guys. Be safe, okay? And I'll see you guys in Thursday. Please do ask questions, okay?
Professor.
Yes.
I actually was looking through my stuff and I found a formula sheet that goes for mechanics and electricity and magnetism. So I was gonna suggest maybe if you want like a what's it called, a scan of it, so you can share it to the class.
Sure. Yeah. Go ahead. Send the Farah. Send it to me. I will look at it, and
Okay.
we use it. I mean, if somebody feels comfortable with it. Usually, when we're doing live class, when I'm doing actually in-person classes, I give all the formulas because you are not required to memorize the formulas. You're required to understand them as far as calc-based courses. So there is no memorization. I mean, I give you all the formulas you want. Trig relationships, integrals, everything you need, okay? Because the point in here, even for that problem that I gave you today, actually on Canvas, the one that is supposed to help you prepare for your exam too, I give you at the end the integrals because I'm not asking you to do calculus. This is not what this class is about. This is not the class also for where to go and try to learn trig identities. This is not the class even where to memorize these formulas that I'm giving you. The journey to them, this is basically Feynman himself. We teach you basically different methods, that's what he says, so that you empower yourself to solve the problems by yourself. Just looking at the formulas at the end, this is not what this is all about. This is about basically applying these things. But do send it for us, please, okay?
Okay, I'm gonna email it then.
Okay, very good. Thank you.
Thank you.
Anybody else has any questions or comments or something or addition? Okay, then I see you guys in a week from today, and be safe, okay? Bye.
Professor, I have a question.
Go ahead.
If we're having a bit more trouble understanding, what outside source would you recommend, like YouTube video?
You have my office hours. Please do let me know ahead of time, and we will meet on a one-to-one and work out whatever basically, especially if it's integrals and things like that. I will record them for the benefit of the class so that the rest of the class also will benefit from that. Unless, of course, we are talking about something unique to you, which in this case, we probably were not going to share it with anybody, including not recording it. So if you guys have that. Honestly, I don't know any other resources better than this book that I was showing you, Feynman. There is a link actually in the syllabus for the lectures. They go in very, very detail, both math and physics. Feynman is known to hammer all of these things. the best people who understand physics there actually learned it from him. I mean, he was the best teacher of physics that I can think of. Nobody that taught physics better than he did. Now, in terms of also applications and math, in terms of this class, I would recommend you do as much problems as you can. That's why I'm trying to give you different ways of doing these things, trying to solve these problems. So if you have any questions, please do ask it. I'll be more than happy to go on a one-to-one or a group of you guys. We'll go live on Zoom, basically discuss these things. And that's what the office hours are for, actually. They are for this purpose. And if you find any other resource, like for us, for example, please do share it so that maybe other people can take advantage of it too. And that's basically what I can tell you.
Thank you, Professor.
No problem. You have to remember that this is physics 4B, which is a little bit harder than physics 4A. It's not a little, so let's make it. It's probably the hardest course that you're going to have in the physics sequence in the college. Maybe probably the hardest course you're going to have at all. Okay, because it's unlike calc courses, which they give you the integral and tell you, okay, this is how we do this integral, and then you start practicing. This one, you have to set up the problem yourself first. In order to get to that integral, there's a lot of work in physics that needs to get you there. And that is where the difficulty with this course is. So this is probably the hardest course. I'm telling you this up front, not to discourage you, but to tell you basically that you really need to put a lot of effort in it. And if you find yourself basically moving along with it, you should really be proud of yourself because you're doing a lot. And I'm already seeing a lot of you already doing a great work in here. Okay?
Yes, sir. Thank you.
Okay. Thank you, Faraz. You sent me a message. Very good.
Mm-hmm.
Okay. Okay. If there is any other question, please. If not, then we will end this session because we went way past the time allotted. Okay. Okay. Bye, everybody.
Bye.